Alright students, so in this video we're going to be solving equations involving exponential functions and logarithms. Just to give you an idea about the type of problems that we're going to be solving, this is in the section of logarithmic and exponential equations. So some of these: solving a multi-step equation involving a single logarithm, problem type 1, and 2, solving multi-step equation involving natural logarithms and solving an equation using logarithms on both sides, type 1 and 2, and then a bunch of exponential equations by finding common bases or by logarithms or natural logarithms. I'm not going to do every single one of these because some of them are very similar and the steps are very similar, and you can identify that. But we're going to do at least 8 or 9 of these different problem types. So real excited. Let's get going. And before we just jump right into the problems, there's a couple of things that we're going to need to remember. For instance, how to convert an exponential equation into a logarithmic equation, where we have b to the x equals a corresponds to log base b of a equals x. We're going to be utilizing that. We're also going to be utilizing the properties of logarithms, specifically the product property log of a times b is equal to log a plus log b. Log of a over b is equal to log a minus log b, and log of a to the c is equal to c times log a. Another thing that we're going to be doing that you may not have seen before, and that is we'll have an equation where we've got something on the left-hand side, something on the right-hand side, and we're going to take the logarithm of both sides. So remember the old whatever you do to one side, you've got to do to the other. Well, that's what we're going to do, and we're going to take the logarithm of both sides. You may not have done that before, but that's a perfectly acceptable mathematical procedure. So let's jump right into it. So here's just a basic logarithmic equation, and we have log base 6 of x equals -2. And the way we solve this type of problem is just first off convert this to an exponential. So it's going to be 6 to the -2 equals x. Remember, when you have a negative exponent, that means we can drop it down to the denominator. So we have 1 over 6 squared equals x. That's 1 over 36, and that's a good answer. So a lot of these first set of problems just convert that logarithmic equation into an exponential and see where that takes you. It might take you somewhere nice. Believe it or not, these 3 problems here, same exact type of situation. Even though we've got some sort of expression here in the middle, we have a logarithm on the left-hand side and a number on the right. So we're going to convert this to an exponential. So 2 to the first equals -5x plus 7. Now we're just looking at a good old linear equation. We're going to solve for x. So subtract 7 from both sides, we get -5. Divide both sides by -5, and you get x equals 1. If you weren't ever sure about this, you could plug that into your calculator or into some maybe website calculator or whatever that allows you to customize the base for easy calculations. Same thing we're going to do here. Convert this. This would be base 3 to the 4 equals -4x plus 10. Boom. You can calculate that. Alright, we also have some problems, however, where the logarithm is not all by itself. And the way we solve these type of problems, well, get that logarithmic term all by itself, or isolate the logarithmic term, or the logarithm term. So in this case, that just means add 8 to both sides. So we now have log base 2 of x plus, but x plus 5 should be x plus 6 there. Add 3 to both sides, or add 8 to both sides, and we get 3 over here. I don't know if I fixed that over here. So so that would be 2 to the third equals x plus 8. It seems that I made another mistake by copying that down. X plus 6, and then it's 5, and then it's 8 over here. But this should be a x plus 6 right there. I'm not really sure what I was thinking on that. Just maybe trying to go too fast. So at this point, though, you could just solve for x. Moving on to the next problem here, we have 7 log base 5 of x plus 27 equals 14. We want to isolate that logarithmic term, and so we'll just divide both sides by 7 and have log base 5 of x plus 27 equals 2. Seem to copy that down properly. And then once again, turn this logarithmic equation into an exponential. That would be 5 squared equals x plus 27. You could multiply that out, subtract 27. I think you know where we're going with all that. So this is a little bit of a different type of equation, different type of equation. This one, some of the other ones, we have multiple logarithmic expressions here on the same side. So one of the ways that we can handle this is, remember that property of logarithms where we've got a log plus a log. So log A plus log B is the same thing as log of A times B. So I'm going to write this as natural log of 4 times x plus 1. And all that inside the natural log equals -1. There are other ways of solving this type of problem, but this is the way that I'm going to do it right here. So I'll then just distribute that 4, so I have natural log of 4x plus 4 equals -1. And then, yet again, turn this logarithmic equation into an exponential. If you remember, the natural log has a base e. Now we don't really write it down there because that's what ln means, is log base e. So if we turn this into the exponential, that's going to mean e to the -1 equals 4x plus 4. We can then write e to subtract 4 from both sides, and then divide both sides by 4, so we get e to the -1 minus 4 all over 4 equals x. Plug that into the calculator, and you get x equals -0.91, rounding to the nearest hundredth. That's what they want. This problem right here, once again, just we've got a 3 here. We'll subtract 3 from both sides. Then we have natural log of x minus 5 is going to equal -1. And we're left with the same sort of situation here. We will convert this logarithmic equation into an exponential. So e to the -1 equals x minus 5. Add 5 to both sides. You can type that into the calculator. Same thing here. We'll divide both sides by 4. Turn that logarithm into an exponential. So ln of 5x equals 3 turns into e to the 3 equals 5x. Divide both sides by 5. Plug that into the calculator, and you'll get a great answer. All right, so now we have a situation we've got logarithms on both sides. Well, no big deal. We want to get all of our logarithms onto one side. Before we do that, just want to make a little note here. If you remember from our discussion of logarithmic functions, we noted that what goes inside the logarithmic parentheses, so to speak, has to be bigger than 0. Logarithms are only defined where what's inside there is bigger than 0. So that means that x minus 6 has to be bigger than 0, which in turn implies that x has to be greater than 6 if you add 6 to both sides to that inequality. This right here, x minus 2, must be greater than 0, which if we add 2 to both sides, that implies that x has to be greater than 2. So if we look at that, x has to be greater than 6, and x has to be greater than 2. So this one right here is a little bit, well, I mean, it's obviously, I'd say this one's more restrictive in a manner of speaking. So it's got to be 6, it's got to be greater than 6. Okay, if it was 3 or 4, then that would not be meeting that qualification. So, all right, this is going to play a role here in a minute. Now let's go ahead and solve our problem. So we're going to get all, I didn't even spell all right. Sorry about that. So get all the logs, get our log on one side. Use the property of logarithms to combine them, then convert to an exponential. So let's go ahead and do that. So I'm going to add this term over here to both sides. So I have log base 5 of x minus 6 plus log base 5 of x minus 2 equals 1. Then using the property of logarithms, log a plus log b is equal to log a times log b. So this is going to be log base 5 of x minus 6 times x minus 2, which is equal to 1. Then we're going to FOIL. And pretty sure I'm going to get this right if slowly. So x times x is x squared. X times a -2 is a -2x. X times a -6 is -6x. And -6 times a -2 is a positive 12. So that gives us log base 5 of x squared minus 8x plus 12 equals 1. Got that part, got that part. Convert this to exponential. So we have 5 to the 1 equals x squared minus 8x plus 12. Ooh, new step. Solve the quadratic. Sometimes we're going to get a quadratic here. So a couple different ways. There are, I guess, 3 different ways you can solve a quadratic equation. You can use the quadratic formula. You could graph it and find the roots. I think in a lot of these, they are set up so you can actually do factoring, which is great because factoring is fast. So subtracting that 5 from both sides turns that 12 into a 7. We have leading term of x squared, so that means I have an x and an x. I need 2 numbers that multiply together. That equals 7, and when combined, they equal -8. So that seems to me like it's going to be a -7 and a -1. which means since I have two things here together that multiplied equals 0, our algebra teaches us that either this thing is equal to 0 or that thing is equal to 0. So either x minus 1 equals 0 or x minus 7 equals 0, which means that x equals 1 or x equals 7. Okay? Now, if we go back up here, we say, aha, haha, x has to be greater than 2. And this one, not greater than 2. But x equals 7 definitely fits both of those criteria. That's our official answer. Hooray. Okay, another problem type. These are what we call exponential equations. And you can look here. All three of these problems kind of look somewhat similar. They've got some sort of base with our x in the exponent location, or so 81 and 27. So these are definitely different bases, 5 and 25. And this one even has x in the exponent on both sides. Okay. So the technique here is we are going to convert to the same base. We want to have the same base on the left-hand side as we do on the right-hand side. And these particular problems are set up so that these are both multiples or powers of the same number. In a minute we'll look and see what happens when that's not the case, but for here we notice that, hey, 4 is a power of 2, 4 is 2 squared, and 8 is a power of 2, it's 2 cubed. So I can write this as 2 squared, just replacing the 4, to the negative x minus 3 power, and I'll write 8 as 2 cubed. Now if you remember your properties of exponents, anytime you have some base to a power and then all of that to another power, you multiply those exponents right here. So that would mean I have 2 to the 2 times negative x is negative 2x, and 2 times negative 3 is a negative 6. Showing that distribution there, equals 2 to the third. So we have 2 to the negative 2x plus, or sorry, negative 2x minus 6 equals 2 to the third. Since those bases are the same, then the exponents must be the same. So negative 2x minus 6 has to equal 3. That's great. We have turned this somewhat complicated exponential equation into just a good old linear equation, which we've been doing forever. So add 6 to both sides, divide by negative 2, and we get x equals to negative 9 over 2. We could do the same thing over here. It kind of helps to know your powers, or at least to maybe experiment with some of them. So this is 81 is 3 to the 4th, 27 is 3 cubed. You're really only going to have powers of 3, 2, 3, 4, 5, 6 in some of these. So let's just go write those off to the side. So I'll rewrite 81 as 3 to the 4th. I'll rewrite 27 as 3 cubed, but all that in parentheses to the power x minus 1. So distribute that 3, and so I have 3 to the 4th equals 3 to the 3x minus 3, distribute that 3. And once again, just go ahead and set this exponent equal to this exponent. So 4 equals 3x minus 3, and I'm sure you can solve that on your own. Now, these problems have our variable in the exponent location, but the bases are clearly not multiples of each other. So we have like 11 and 7 and 6 and 11. I should really like 11 a lot. So here's where we're going to introduce this sort of, well, I guess it's not that interesting of a technique. We're just going to turn this exponential into a logarithm equation, which is kind of funny. Before we had the logarithm equations, we solved them by turning them into exponentials. Now we have the exponentials, and we solve them by turning them into logarithmic equations. But anyway, base 11, so log base 11 of 7 equals y plus 4. And then we'll just subtract 4 from both sides, so we have log base 11 of 7. I'm going to put that in parentheses to make it very clear that it is the log of 7 minus 4. That 4 is not inside the logarithm term. This is a number all unto itself. Okay? And you're like, well, how do I type this in or whatever? Well, recall that is, I probably should have put this in the very beginning of the list of stuff we need to remember in order to solve these problems, but I didn't. Anyway, if you have the log base a of b, that's equal to ln b over ln a. That was the change of base formula. So we can find log base 11 of 7, turn that into ln 7 over ln 11 minus 4 equals y. I can plug this into the calculator all day long, and I get y is equal to negative 3.19, rounded to the nearest hundredth. All right, getting close to the end here. Same kind of thing here, but I've got this is an exponential on the left side, exponential on that side. Clearly those bases are different. So we can't just say we can't just turn this whole exponential into a logarithmic equation. I guess we could try it, but I'm going to show you a technique that's going to work every time. So with this kind of situation, we're going to take the log of both sides. So this is something we never even thought about doing. Sort of like adding 5 to both sides, or dividing both sides by 2, or taking the square root of both sides. We're going to take the log of both sides. All right, let's do it. So 7 negative 3x and 11 to the negative x plus 6. We're going to take the log. They're kind of telling us here a little bit of a hint here. Write the exact answer using base 10 logarithm. So I'm going to write log, and I'll write log here, and we all know that I'm implying base 10. So log of left side equals log of right side. Then use properties of logarithms. We know we can pull that exponent out, so we have negative 3x times the log of 7, and we can pull this out here. This should be a negative x plus 6. I think I fix that here in a second. All right. So distributing this log 11, so yep, there it is. So log 11 times negative x is negative x log 11 plus 6 times log 11. And then I'm going to get all my x terms on one side, and I think that's going to be the left-hand side. So negative 3x log 7 plus x log 11 equals 6 log 11. I have an x in both of these terms, so I'm going to factor it out. Negative 3 log 7 plus log 11 equals 6 log 11. And then, you guessed it, divide both sides by negative 3 log 7 plus log 11. So that dot 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 means negative 3 log 7 plus log 11. And I divided by the same thing over here, which gives me a nice final answer of 6 log 11 over negative 3 log 7 plus log 11. All right. Before I finish the happy face here, I'll say that just to wrap things up, we solved this problem by taking the logarithm of both sides. We solved a lot of those other ones by converting the exponential to the logarithm, or the other way around. All right. Hope you enjoyed this. Good luck solving these problems and similar problems on your own.